Okay friends, let us see polyvinyl chloride. The polymer has the following structure. We all know CH2CHCl. The monomer vinyl chloride boils at minus 14 degrees Celsius. There are two methods for the production of vinyl chloride. One is by cracking ethylene dichloride in vapor phase, and the other is by reacting acetylene with hydrogen chloride in the presence of catalyst, the well-known addition reaction of acetylene. So let us see the first one, wherein ethylene dichloride is cracked in vapor phase. This is ethylene dichloride, vapor phase, 500 degrees Celsius. We get a hydrogen chloride, okay, and we get vinyl chloride. Another one is the reacting acetylene with hydrogen chloride. 150 degrees Celsius in presence of catalyst, we get vinyl chloride monomer. Industrial polymerization of vinyl chloride is carried out either in suspension or emulsion. Limited quantities of PVC are also made by bulk polymerization. Okay, so limited quantities of polyvinyl chloride are also made by bulk polymerization. Redox initiators are used for emulsion systems, where azo compounds are employed in bulk and suspension techniques. The emulsion system has the advantage that the polymerization could be done at low temperatures, say 20 degrees, whereas high temperature 80 degrees to 50 degrees, 50 to 80 degrees are required for the suspension in bulk. So, you don't have to go to high temperature when you are using immersion technique. Since the monomer is a gas at this temperature, polymerization has to be conducted in pressure reactor or in autoclave because the boiling point is quite low. Structurally, the PVC molecule is partially syntactic and does not have complete regular structure. This is why PVC has low crystallinity. The polymer molecules are either linear or only slightly branched. PVC is insoluble in vinyl chloride, alcohols, water, and hydrocarbons. Acids and alkalis have practically no effect on PVC, at least up to 20 degrees Celsius. PVC, however, dissolves in ketones, chlorinated hydrocarbons, and the mixture of acetone and carbon monoxide is found to be excellent solvent for PVC. Extremely sorry for the noise, but work is going on, so we can't help it. PVC is one of the cheapest and the most widely used plastic globally. It is used for the large scale production of cable insulations, equipment parts, pipes, laminated material, and in fabric manufacture. PVC is thermally not very stable, and beyond 200 degrees Celsius it degrades with the evolution of hydrogen chloride. This is further attended by the formation of conjugated double bonds along the chain, which will result in the discoloration of the polymer. To avoid such discoloration, a suitable stabilizer is added to the polymer. The usual stabilizers are alkali, earth oxides, organometallic salts, epoxy compounds, and amine type compounds. PVC as such is a horn-like material and difficult to process. It is therefore compounded with plasticizers. Depending on the plasticizer percentage, fully rigid to highly flexible finished product can be obtained. In many cases, plasticizer content may be up to 30% by weight of the product. Polyvinyl chloride finds excessive use in certain formulations called plastisols or organosols. These are paste-like compositions and are produced from emulsion polymerized PVC resin particles. Plastisols are produced by disposing PVC particles into plasticizers. The organosols, on the other hand, are produced by disposing PVC particles in a suitable mixture of volatile organic liquid and plasticizers. Plasticizers and organosols also contain other compounds such as colorants, fillers, growing agents, and stabilizers. At ordinary temperature, the PVC particle present in plastisol or organosol does not dissolve the liquid medium, but only remain as viscous system. When the temperature is raised to 150 to 200 degrees Celsius, PVC fuses with the plasticizers and form physically cross-linked structure in the shape of the ultimate plastic article. The total chlorine contained in PVC is around 56.8% and can be increased further to 60 to 65% by dissolving it in a suitable solvent such as chlorobenzene and chlorinating at 100 degrees Celsius. The polymer thus formed is called chlorinated PVC. It is assumed that during chlorination the chlorine replaces the hydrogen atoms in H2 units rather than in the CHCl units of the molecule. The principal advantage of chlorination is that the polymer becomes more resistant to acids and bases. However, the stability towards heat and light is found to decrease. The main advantage, the main use of chlorinated PVC is in the manufacture of adhesive, coatings and fibers. So this is all regarding PVC. Okay. Now let us see acetylene. Okay. Acetylene itself is formed by the reaction of inorganic compound calcium carbide CaC2 with water. CaC2 plus 2 molecules of water giving C calcium hydroxide and acetylene. This method was once important industrial process for the manufacture of acetylene. However, the method has now been replaced by a process in which methane is pyrolyzed in a flow system with short contact time. So this is one of the method of preparation of acetylene, and the properties are acetylene is non-toxic, colorless and odorless gas. However, commercial grades contain impurities that tends a garlic-like odor to the gas. Commercial manufactured through a reaction of water and calcium carbide. The moisture content of the industrial gas is less. It is also a byproduct of clean production. So this is all regarding acetylene. Okay, thank you.